Thank you for the invitation. I'm very happy to be here and have a chance to talk to you. I'm Michael Karamanis. I teach in the College of Engineering, so one of the few sort of card-carrying engineering speakers here. And my area is systems engineering optimization, which is the cyber part of the cyber physical system that energy systems are like today and are progressing to be in the future. So everybody talks about renewables, everybody talks about electrification, changes on the way that we consume electricity, but I do not think that we speak enough about how those two interact and how this cyber physical system, the cyber in the sense of information, coordination, control, and so on, and physical in terms of wires, of batteries, of generators, renewable generators, and so on, can coordinate. So here is first a very quick view on how these things interact. So you have the wires, you have the transmission and distribution system. Transmission system is the high voltage lines that you see out there, where when you drive in the open, in the countryside, and large generators and large consumers are connected to that. Conventional generators are coal plants, natural gas plants, but also more prevalently wind farms and other renewables. Now, one of the ways that these interact is through losses and through congestion. So it's possible that a line in this huge transmission network is congested and you can't absorb more cheap renewable generation, because electricity has the nasty habit of following the laws of physics, and in going from A to B, travels over all possible paths in proportion in inverse proportion to losses across those paths. So if there is a line in any one of those multiple paths that you can use to go from A to B that's overloaded, then if you try to extract more cheap electricity at A and feed load at B, some of that will go over the line that's congested, and bang, you can't do it anymore. So then the issue is how to deal with that by changing dynamically the interconnection, the architecture of the transmission network at the distribution level, which is becoming more and more important, because this is where the cars are going to be, the electric cars are going to be. This is where a lot of renewable generation is going to be. We have a lot of interaction in terms of the transformers and the assets of the distribution network degrading or not being up to par if the transmission, if the renewables and let's say the electric cars do not coordinate. So being able to match this, being able to have cars charge not at the same time so that they blow up transformers, be able to have to get photovoltaics to assist with the control of the voltage and the quality of power is very important. So how do we do that? The suggestion to do that is by trying to calculate, to understand the marginal cost of consuming and generating electricity at various points of the network that represents the actual marginal costs of the transmission, the distribution system, and these new loads. So being able to do that is very important, and systems theory allows us to do that. Computer science allows us to do that. Electronic platforms allows us to do that. So we have to study and see whether this is possible, and also, of course, investigate the impacts, the socio-economic impacts of going forward in this sort of coordination. Thank you.